Welcome back. We're going to dive into Chapter 7, Part 3, Pyruvate Oxidation and the Citric Acid Cycle. Starting out with pyruvate oxidation, we ended glycolysis with 2 molecules of pyruvate, and pyruvate does not itself enter the citric acid cycle. It has to be converted into acetyl-CoA. This will only happen if oxygen is present. So when oxygen is present, pyruvate will be able to enter into the mitochondria to complete the oxidation process. In the process of going through pyruvate oxidation, we have release of our first molecule of carbon dioxide. Remember that we do this twice, one for each pyruvate molecule that comes off of the glucose. So in the end here, we are getting 2 molecules of carbon dioxide coming from this process. We also go and take NAD plus and we make NADH. Of course, that's also happening twice. The third thing that happens is that we get something called coenzyme A, and you can see right there it's just called CoA when it's attached to this group right here. So we have our final molecule called acetyl-CoA, and acetyl-CoA goes into the citric acid cycle. Coenzyme A does what most coenzymes do. They're not really used up in the process. They just help the process along. So the citric acid cycle is sometimes called the Krebs cycle. So if you're looking up animations maybe on YouTube and they refer to this as the Krebs cycle, you'll know what they're talking about. The citric acid cycle is going to completely break down the rest of pyruvate into carbon dioxide. And we're going to do this a couple of times, once for each pyruvate molecule that was made at the end of the glycolysis. So the cycle does turn twice, and in total, we generate 2 ATP, 6 NADHs, and 2 FADH2s for every single glucose molecule. If you want to do the math on that really quickly, one cycle does 1 ATP, 3 NADHs, and 1 FADH2. I also wanted to give you a quick reminder that you have those animations online right there. That's just a reminder that if you're having difficulty following everything that I'm talking about in this lecture, if you check out the animations, you might be very, very happy with the information that's provided there. It's the same information that I'm providing, but it's showing you in a step-by-step process, which is always nice. All right, so let's go ahead and look at the citric acid cycle, because we've covered pyruvate oxidation in as much detail as we're going to cover it. So again, this is happening in the cytoplasm. In the matrix, not in the cytoplasm, in the matrix of the mitochondria, which is kind of like the cytoplasm of the mitochondria, but that's a different term. So remember that for every pyruvate, we had 1 carbon dioxide, and we use up 1 CoA, we make 1 NADH. So here we have our acetyl-CoA. And the first thing that happens in the citric acid cycle is that the acetyl-CoA is going to be released. The CoA part, the coenzyme A, is going to be released. And just looking at the overview here, we're going to have those 2 carbon dioxides released. We're going to have, for each turn of the cycle, we're going to have 2 NADHs made. We're going to have 1 ATP made. And we're going to have 1 FADH2 made. And then there's our last NADH that's made. So a total of 3 NADHs, 1 FADH2, and 1 ATP. Again, with pyruvate oxidation, this is the leftovers from glycolysis, and that's happening in the matrix. The rest of it is the citric acid cycle, and we're going to get some details of the citric acid cycle. Sorry about that. We're going to get some details of the citric acid cycle at this time. So we have 8 steps to the citric acid cycle, and each of those steps sorry about that. And each of those steps is involving a specific enzyme. I think we're getting kind of used to that so far because we were looking at specific enzymes in glycolysis too. So the acetyl group of the acetyl-CoA joins the cycle by combining with something called oxaloacetate, and we're going to form citrate from that. That's why it's called the citric acid cycle, because citrate is the first thing that's formed in the citric acid cycle. The next 7 steps are going to finally break down that citrate, but what it's going to do is it's going to regenerate oxaloacetate. And that's why it's a cycle, because the first thing that enters it, oxaloacetate joining with that CoA, is going to, it's all going to reform, and oxaloacetate is going to come back to us in the end. The NADH and FADH are eventually going to take those electrons that they took from the glucose molecule or the pyruvate molecules, and it's going to run them into the electron transport chain that we'll get to in the next lecture. So, citric acid cycle. Lots of details here. I'm going to go ahead and show you just the kind of blown up version of this because this is a little hard to see. So there's our citric acid cycle, and let's start out at the beginning here. And if you need me to run back to this and show you the big picture again, we can do that, but we're just kind of focus on each little part of this. So again, starting out here with our acetyl-CoA joining up into the citric acid cycle. It's going to join to oxaloacetate, and it's going to release that coenzyme A. That's going to go, and it can be reused again to join up with the pyruvate, and so it gets used over and over again. So oxaloacetate causes the CoA to be released, and it does form citrate as the first product of the cycle. The next thing is that citrate is going to be rearranged into isocitrate, and that's going to cause the release of some water. As we're moving along looking at this, isocitrate is going to be rearranged, and it's actually going to release some carbon. So it's going to go from having 1, 2, 3, 4, 5, 6 carbons right there. It's going to be rearranged to 1, 2, 3, 4, 5. And so we've lost a carbon dioxide. We're also going through redox reactions, so we're going to make some NADH. This new molecule after isocitrate is alpha ketoglutarate. And when alpha ketoglutarate is changed through its process, we are going to add in a coenzyme, as you see here. But we're also going, and there's the coenzyme right there. So it changes the name to succinyl-CoA. We're also going to be making an NADH as a process, or as a result of doing some more redox reactions. After we get our succinyl-CoA forming, we're going to then change and make, well, one of the things we're going to do is we're going to release that coenzyme A. And so the coenzyme A is released right here. And in that process, it's a little complicated. We're not going to go into these details, but we do make our first ATP right here. And notice that when succinyl-CoA loses its coenzyme A, it's called succinate. Then we're going to go through another series of redox reaction right there and make FADH2. Succinate is going to be oxidized, and FAD is going to be reduced. And if you look at how many carbons we have in our next molecule, it's 1, 2, 3, 4. And that molecule is called fumarate. So when fumarate happens, and fumarate's made, again, that's the 4-carbon molecule right there, water is going to be added back into this, and we're going to make a molecule called malate. The final thing that's going to happen is that malate is going to go through its oxidation, and in that process it's going to reduce NAD+ to make NADH. When that happens, we regenerate our oxaloacetate, and our oxaloacetate has 4 carbons. Remember, we talked about that just a minute ago. So this is the big picture again. We start out with oxaloacetate joining with acetyl-CoA, 1, 2, 3, 4 carbons here, 2 carbons there, giving us a 6-carbon citrate, and going through a series of reactions where we harvest 1, 2, 3 NADHs, 1 FADH2, and 1 ATP. Notice again that this is going to go through twice for every single glucose molecule that enters glycolysis. So our totals are 6 NADHs, 2 ATPs, and 2 FADH2s. That's all I'm going to talk to you about for the citric acid cycle. We're going to move on to our next part, which is oxidative phosphorylation. That's made up of the electron transport chain and chemiosmosis.